Okay, so here we go. We're going to try to squeeze in, 20, 25 minutes of math after the test today. New chapter. Very exciting. Vector calculus is some of the most geometrically interesting material in the course. I always look forward to chapter 6. It's the most fun material for me. First, I'm going to say that I'm going to present this material in a way that's a little bit different than a lot of textbooks do it. There's a tough choice to be made, and I have my own answer to how to deal with that. So the first thing I'm going to start off by pointing out is that I cannot give you a full discussion, complete discussion of the big theorems that we're going to be talking about here in Chapter 6 because it's just too much. It's arguably graduate level to really do it right. So there is a big theorem called the Generalized Stokes' theorem that encapsulates all the big theorems that we're going to talk about in Chapter 6. All of them are special cases of this one theorem called, Generalized Stokes' theorem. There are a bunch more theorems that we're going to talk about that kind of relate, that appear at a glance, the way we're going to see them here in this course, as individual theorems, but which again, they all could be viewed as, from a certain point of view, special cases of this one more general idea called the Dorama homology theorem. It too, much more sophisticated than we could possibly discuss here in Math 212. Okay. All right, so what are we going to do about that? Well, one thing we can do, and what a lot of textbooks do, is just don't talk about that structure. Don't talk about the unification of these individual theorems. And a lot of textbooks present the various big theorems in Chapter 6 as just independent, separate, distinct, unconnected, unrelated theorems. And you can do that, and it's fine, and it's true, but man, it misses out on a lot of really amazing opportunities. The fact that these theorems are all special cases of the same big unifying theorem has consequences. And one of the big consequences is that these theorems, these individual separate theorems, there's a strong analogy between them. Well, at a minimum, even without discussing the great big sophisticated theorem, we can still talk about, but you see the patterns, see how these theorems all, in many ways, they have a lot in common, they follow the same structure, that kind of thing. So this is what I'm going to try to do in this course. Rather than just present them as separate theorems, end of conversation, I'm going to try to emphasize the analogies between the theorems. There is a structure that you can make which is very sophisticated and far more than we could reasonably discuss in this course, which I'm going to give you a watered down version of. I'm going to take away all the rigor and precision and leave something that hopefully is more at least relatable. But the point is, I want you to see how these theorems fit together, if not, the details of, the actual connections. For that, again, that's far too much. Can't reasonably do it. So this is my compromise approach. And so we're going to see motivations for the theorems, not proofs. We're going to have a language and a framework that are suggestive of the big relationships between these objects, even though we're not going to talk about the actual relationships. Okay, so I emphasize this is not going to be a rigorous conversation. I mean, when I'm talking about the framework and the connections and this kind of thing, it's going to be just kind of a discussion of analogies. This framework, it comes out of, I'm stealing it from a very rigorously and precisely defined thing, but it's not going to be precisely defined in this course. Again, that would kind of defeat the purpose. It would be a little too hard. Okay, so I just wanted y'all to sort of know that context. Here is a picture of various objects that we're going to be considering here in Chapter 6. before I go through and enumerate what these objects are, let me just remind you, why are we considering these objects? And the answer is because these are the objects which, as it turns out, are powerfully related by the generalized Stokes' theorem, right, that we can't talk about. Okay, so this big theorem that I can't actually tell you has as its special cases statements that take place on the following kinds of domains. It just does. So a certain amount of this conversation is, again, y'all are going to have to sort of take my word for it as to how these things come up. So we're going to be considering intervals on the x-axis, which, of course, as you know, have boundaries that are points on the x-axis. We're going to be talking about two-dimensional regions in R2, the boundaries of which are curves in R2, the boundaries of those of which, of course, are points in R2, etc. We're going to be looking at solid three-dimensional things. We're going to be looking at surfaces, curves, and points in R3. Okay. All right, now what are we going to be doing on these objects? What the generalized Stokes' theorem says is a statement about certain kinds of integrals which, when you look at these special cases, involve, again, here's how it turns out, take my word for it, single variable integrals, double integrals, on curves in R2, vector line integrals. Very important. Not scalar line integrals. That's just not what the general Stokes' theorem talks about. It just isn't. Right? So, now I want to emphasize, it might appear that I'm making some sort of an arbitrary choice here, that I'm choosing to think about vector line integrals. And okay, maybe, I suppose, but the point of view I want y'all to take is, I'm making this choice, if any, to choose to talk about vector line integrals specifically, because that's what the general Stokes' theorem talks about, as it turns out. Okay, so you don't need to know why we're going to talk about vector line integrals instead of scalar line integrals. You just need to know that we're talking about vector line integrals. Okay, likewise, vector line integrals on curves in R3. On surfaces in R3, we will be discussing vector surface integrals, not scalar surface integrals just aren't going to come up to speak of in this discussion. And then on solids, of course, triple integrals, plain old, good old, regular old triple integrals. Okay, so those are the objects that we're going to be discussing. Those are the types of integrals that we're going to be evaluating. I'm calling these evaluations in this context. By the way, we'll also, just for sort of organizational purposes, I'm going to consider points in whatever context to be kind of sort of domains in a way. And rather than evaluating integrals on these domains, we're going to evaluate. I give you a function and a point. You can take the point, plug it into the function. It's not exactly an integral, right? But in both cases, whether you're talking about an integral or just plugging into a function, there's a set that you might think of as a domain, and then there is a, how do you evaluate something on that domain? Okay, so this is the context. That's what we're going to be talking about. Okay, you'll recall that some of these things are oriented. Let me come back over here. Right, if we are talking about a flux integral, right? It's not just a surface; it's an oriented surface. If you want to talk about flux through a surface, well, flux in which direction? Likewise, if you want to talk about a vector line integral along a curve, well, which way on the curve? Are you going this way? You're going that way. They're very different questions. Okay. The amount of work it takes to drive uphill, not the same as the amount of work it takes to drive downhill. In fact, reminder, in both cases, the choice, which way, what's the orientation on the surface, that describes the flux that you're going to compute, or which way are you going to be driving along this road to compute work. In either case, the orientation dictates a minus sign. Right, so the difference between how much work it takes to drive that way versus how much work does it take to drive that way, the difference is exactly the negatives of each other. Right? Likewise with flux. Right? If you change the orientation, remember we talked about if you accidentally parameterize your surface the wrong way, well, that just means you have your normal vectors backwards, namely exactly the negatives of each other, and the flux will turn out to be exactly the negative. Okay, so as of the moment, we think of orientation as being something geometric, right? So I think of orientation, on this curve to be a choice between, that direction versus this direction. I think of the orientation geometrically. Those are my two options. Likewise, over here, on a surface, I think of my orientations as, well, I can choose to compute flux that way through the surface or that way through the surface. And I think of this choice as a geometric one. Which direction is the flux? So I want to broaden that idea now a little bit. Observe that in both of these cases, the choice, while it is geometric, and you can think of it geometrically, we can also think of an orientation simply as a convention, the consequences of which are a minus sign. Right? So that's going to be our going forward, our sort of broadened notion of what we mean by an orientation. It's a convention that involves either a plus or a minus. Okay. All right. So, some of these ideas you can kind of see coming. Like we already know. I guess I didn't. Well, okay. We already know, let me write it down over here, that the integral on this curve, the integral that direction, is the negative of the integral in that direction. Okay. How am I going to define an orientation on a two-dimensional region? There's no geometric way to think about this particularly. I'm just going to define the orientation as again, there's going to be two choices of your orientation. There's no picture. The orientations are either plus or minus. Now, those are conventions. I don't know. I can't draw a picture of them. I don't know what they look like, right? But it's a convention. I can either say this is positively oriented, or I can say it's negatively oriented. And what I mean by it's going to have a consequence of a minus sign in the evaluation is just this. If you have a negative orientation on your two-dimensional region, what I mean is the double integral evaluated over that negatively oriented region, the double integral is just the negative of the otherwise double integral. I emphasize, I'm making stuff up here, right? You should be highly suspicious at this point that this has any use or value. I certainly haven't communicated any so far. Yeah? Okay. Nevertheless, this is a definition, arbitrary and pointless, though it may seem that's going to be useful. So likewise, if you have a positive orientation on your two-dimensional region, all that means is that when you evaluate the double integral, multiply by positive 1. In other words, positive orientation is you might say, the default. Okay, so likewise for triple integrals. Likewise for single variable integrals. Analogously, right? Likewise for plugging points into functions. Now, this one here is a little bit confusing for students sometimes, and that's natural. Let's look at this right here. It's tempting to look at this minus and think, oh, well, I am plugging in then into this function f. I'm plugging in a point whose coordinates appear to be negative x comma negative y comma negative z. And yeah, I mean, you can forgive the student for thinking that, right? Because there's a minus and then there's the x, and it looks like you're multiplying. Very importantly, we're not. This is not intended to suggest that we're looking at the scalar vector product of negative 1 times x. The quotes here, my reminder, emphasis, that we're just assigning a negative orientation to this point x with coordinates x comma y comma z. So what we mean by plugging in into a function a negatively oriented point, what we mean is plug in the point x, and then we multiply the output value by negative 1, because that's what the negative orientation means. All right, is everybody on board? Okay, so just to emphasize, this here does not mean f of the vector negative x. Okay. All right. Okay, so related to this, we're going to use this in notation. So I'm going to talk about line integrals over a curve, and then I might write a negative sign on the curve. Right? And so whenever you see this, whenever you see something that looks like this, you're like, okay, this is not just a name of a curve. There's an additional, minus sign. What this means is I'm going to evaluate the integral on the curve, and this says, look, whatever the orientation on the curve is, what I meant by this integral was do the integral with the opposite orientation of whatever is the orientation on C. Right? If C is counterclockwise, this means, actually clockwise. Right? So the orientation is just going to be a way of saying go around the other direction, go whatever is the opposite of the orientation on C itself. And so the integral over a negative oriented, a negative on the orientation of C means just take the negative of the value of the otherwise integral. Everybody on board? Okay. Now I emphasize in this discussion here, the curve C, it's a curve. Its orientation is neither negative nor positive. Curves are oriented with geometric ideas. They're oriented, you might say, counterclockwise or clockwise. Right? There's no such thing as positive and negative on the curve itself. But negative C means the opposite of whatever C is. Okay. All right. Let me take a quick pause. Does anybody have any questions so far? I'm asking you all to sort of digest a lot without telling you, giving you any indications of what we're going to do with this or where it's going. But okay. All right. Okay. Also, we're going to talk about this odd little idea right here of adding a curve to another curve. Now, you could come up with some sort of vector-based idea of what this ought to be. Like maybe we're going to take the points, the vector locations on this curve and the vector locations on this curve, and maybe we're going to add those two curves up. And that's not at all what I mean. We're not going to actually add the points in these curves. This means, as a domain, simply this plus just means that we're going to add the otherwise integrals on those two individual domains. So C1 plus C2 as a domain just means, well, if you evaluate on C1, you evaluate on C2, and add them up. Fair enough? Just a choice. Okay. Okay. Alrighty. So now I need to talk about this idea of boundary. We've used this word boundary a lot so far in this course. Different reasons, different purposes. I am now going to talk about boundaries and how they relate to orientations. And there's a bunch of conventions here. These are arbitrary conventions. Side note, we've already ventured into the arbitrary, right? This is a bunch of arbitrary rules that we're just making up, right? The choices that we're going to make here are again going to be arbitrary, seem arbitrary, and by the way, are kind of a little bit actually arbitrary. However, these are not 100% arbitrary. Reminder, everything that we're doing here is kind of, we're trying to follow in the footsteps of this great big theorem, the General Stokes' theorem, right? And the General Stokes' theorem makes a certain kind of a convention, and the consequences of that convention are a bunch of little individual conventions that we're going to be seeing here. So technically, yes, there is an arbitrariness to this, but it's an arbitrariness that got chosen, many years ago. Not as many as you'd think, by the way. The big ideas of the generalized Stokes' theorem didn't really get fully pounded out until the 1950s. It's very recent in the big scheme of things. I mean, most of the math that you've ever learned is at least a couple of 100 years old, right? But not this. This is recent. I think it's really exciting. Right? I mean, I have met people who have met the person who came up with this. Right? It's pretty cool. But anyway, a bunch of seemingly arbitrary conventions. Here's the first one. Now remember, we've talked about intervals. Intervals on the x-axis. This is a familiar domain. Y'all have done a bazillion integrals on these kinds of domains. Right? So, if I have such an interval, now again, keep in mind the orientations, what does it mean to have an orientation on this interval? The orientations are either plus or minus. Right? We don't really talk about, oriented that way or oriented this way exactly. So our orientations are plus or minus. So now, reasonable question then, this oriented interval has a boundary. The boundary consists of these 2 points. Those points should have orientations. Well, which are they? If this is a positively oriented interval, does that mean that both get a positive orientation? Maybe. I don't know. What's the rule? Right? Here's the rule. If you have a positively oriented interval, the rule is that the boundary points A and B get oriented like this. The right endpoint gets a positive orientation. The left endpoint gets a negative orientation. Now says who? Okay, well, it says, look, this is the convention that gets made in the General Stokes' theorem, and they make this convention because if we make this convention and conventions like it, wonderful, powerful things are going to result, right? So we're making this choice, again, to follow along in the path that leads to good things. It is an arbitrary choice, but it's a really clever, as it turns out, really clever arbitrary choice. Okay, so positively oriented interval. The convention is, and by the way, keep in mind, we're talking about what the word boundary means. When we say boundary of a positively oriented interval, we mean a right endpoint that's positively oriented, left endpoint that's positively oriented. Okay. Okay. Now I look at the clock, I see that we are kind of out of time. So we didn't get much done today, but this is still going to be very useful to us. So we will pick up here on tomorrow. See y'all then. Have a good day.